Welcome back. Now that we have gone from rectangular equations to polar equations, we are going to convert the other way and go from polar equations to rectangular equations. And if you see any movement in the background, there's one of my, here's one of my cats. That's Gatsby chilling in the windowsill. So if you see movement, that's what it is. But here we go. Gonna flip this guy around again. So just like going from rectangular to polar equations, the key lies in the four relationships we established when we were just converting coordinates. The first two were the focus of rectangular to polar, and then we added in these other two. Now, before we actually get into the converting of polar equations to rectangular equations, I want to talk about other ways that these equations can be expressed that could also be helpful when we convert from polar to rectangular equations. So if we start with a polar equation, typically, always, we are going to see r's and thetas, and we want to get rid of all those r's and thetas and trig expressions, trig functions, and we want to leave everything in terms of x and y, having a rectangular equation. So we may see something like this where we can use a substitution. If we see an r cosine theta, then we can substitute x. But this equation, if I divide both sides by r, gives us x divided by r is equal to cosine theta. Sometimes we may not see that r is a coefficient of cosine, so sometimes we may just see cosine, and making this substitution, yes, it includes an r and we don't want an r. If we're ending as rectangular, we want to end with x's and y's. We want to end with x's and y's, not r's and thetas. But sometimes if we see a cosine, making this substitution will help, and then we can deal with the r later. So similarly, the second equation, if I divide both sides by r, will leave us as y divided by r equals sine theta. Very similar again to the first one. The third equation pretty much is what it is. If we wanted to square root both sides, I suppose we could do that. Keep in mind, if we square root both sides, square rooting the right side because of that plus sign, because we have two different terms, square rooting the right side does not simplify to x plus y. So keep that in mind. It would just leave the right side with the square root of x squared plus y squared. And I suppose there could be instances where that is helpful, but typically not, so I'm just going to leave it as is. And our last equation, keep in mind, inverse tangent is how we canceled out taking the tangent of theta on the left. So this last equation could also be written as tangent of theta is equal to y divided by x. Now, really, as long as you have these four relationships tucked in a corner somewhere on your paper, you're good to go. But being able to rearrange those, just like we rearranged our trig identities, being able to rearrange those original relationships could be beneficial. Okay, so we'll do three examples together, then I'll let you all practice. So our first example, I'm just going to mark this here, example 1. Well, let's go with the polar equation r equals 3 cosine theta. R equals 3 cosine theta, and our goal is to turn that into a rectangular equation. So all the r's need to disappear, all of the thetas need to disappear. And typically, if the thetas are going, then the trig functions are going as well. So looking up here, what do I notice? Well, I have nothing that says r equals. So I'm probably not going to substitute anything for r. We'll have to deal with that later. My focus is really going to be on this cosine. Looking at this first equation, that is where I have a cosine relationship. But that cosine does not have the letter r in front of it, or the variable r. It has a 3. So I'm actually going to jump over to this variation. Cosine of theta is equivalent to x over r. Cosine of theta is equivalent to x over r. So I'm going to make that substitution of x over r in for my cosine of theta right here. So rewriting that, that means cosine theta, again, we're going to make that substitution x divided by r. So is this a rectangular equation yet? Answer is no. Rectangular equations leave us with only x's and y's. We still need to get rid of the r. We got rid of the theta. We need to get rid of that r. Okay, so how are we going to do that? Well, let's simplify. We have parentheses. How do I multiply? Well, multiplying fractions top with top, bottom with bottom. Keep in mind that 3 really means it has a denominator of 1. So we have 3 times x, which is 3x, and in the denominator, we would have 1 times r, which is r. Okay, well, most of you would say we don't like fractions, so how do we get rid of that fraction? I'm going to multiply by the denominator on both sides. R times R is going to cancel. That leaves us with R squared is equal to 3x. Again, is that rectangular yet? Answer, no. I still have an R. But take a look at how that R is expressed now. Sorry, trying to move my paper underneath my computer here. We have R squared, and we have a substitution for R squared right here. Back at the beginning, we didn't have a substitution for R by itself, but we do have a substitution for R squared. R squared is the same as x squared plus y squared. So I'm going to take out that R squared. X squared plus y squared is equal to 3x. Now, at this point, we don't have any more thetas, so we don't have any more r's. Technically, this is a rectangular equation. Now, as we know, if we are going to type any sort of rectangular equation into our calculator, we want it in the form of y equals, ignore my calculator screen if you can even see it. We want it in the form of y equals, we want it in the form of y equals to type it into our calculator. This one is not going to be fun to get y by itself because, and many of you may notice, if I subtract the 3x to the left side, this is actually the rectangular equation form of a circle. And we know circles, trying to get it in the form of y equals really, really difficult. Again, we have that app in our calculator that allows us around that, not having to get y by itself. But circles are one of those equations that are actually more easily represented in polar form. Excuse me. Wow, I'm getting my words mixed up. I'm sorry. Circles are one of those equations that are actually more easily represented in polar form. But this polar equation, r equals 3 cosine theta, is the circle that has the rectangular equation x squared minus 3x plus y squared equals 0. Okay, let's try another one. Example 2. And these are exactly from slide, 9, 10, 11, slide 11, if you're looking at the slides. So we're going to go with r equals -3 secant of theta. Okay, so the biggest thing that stands out to me is secant. There are no relationships that have been established that involve secant. So all of those identities that we learned early on in trig, those are still going to still play into what we are dealing with. Secant, we know, is the reciprocal of cosine. So while there are, again, no secant relationships, knowing that secant and cosine are related is going to be really helpful. Using the reciprocal identity, I am going to express secant, I still have that -3, secant as 1 over cosine theta. Now, simplifying that up a little bit, again, similar to example 1, I'm going to multiply this out, top with top, bottom with bottom. So I really just have -3 over the cosine of theta. And again, similar to example 1, nobody really likes fractions. So in order to get rid of that fraction, I'm going to multiply both sides by cosine of theta. Cancels out on the right. And just doing a little bit of rearranging. I don't want that r to somehow get mixed up with the angle itself. I'm going to move that r on the right side to be a coefficient of cosine. So I have r times cosine theta equals -3. So now we were able to turn that secant into cosine. And getting rid of the fraction, hopefully this stands out to you, r cosine theta. That's a relationship we've seen. Our goal, again, this is a polar equation we started with. It has r's and thetas. That's how I know it's polar. We want to end with x's and y's. And r cosine theta, right up here, r cosine theta, that is equivalent to the rectangular coordinate x. So I can literally take out all of this on the left-hand side. R cosine theta is equal to x. And making that substitution, we simply have x equals -3. We're done. We have no more r's. We have no more thetas. This polar equation probably could more simply be expressed in rectangular form as x equals -3, the vertical line that runs through an x value of -3. Okay, one more. Let's make it a little bit more difficult, shall we? Example number 3. We have the polar equation, and if you're looking at the slides, I'm going to rewrite it. Trying to type in math on Google Slides is really terrible. So rewriting it here, r divided by 3 tangent theta equals sine theta. And we are going to convert that polar equation to rectangular form. Okay, substitutions. What substitutions can we make? Well, we do have a way of expressing tangent. Yes, I have a 3 in front of the tangent, but tangent theta itself, we can substitute y divided by x. Similar fashion, I have no r in front of sine, so I'm not going to use this form, but I can use this form. Sine, I can substitute y divided by r. So I'm going to come back down here, and I'm going to make those substitutions. We still have r in the numerator. Again, we have no direct substitution for an r by itself. We have r squared substitutions, but not r. So tangent, we said, is y divided by x. And sine is going to be y divided by r. Y divided by r. Okay, so we got some simplifying to do. Here goes. I'm first going to get rid of these parentheses right here. Top with top, denominator of 3 is 1, bottom with bottom. So we have r divided by 3y over x is equal to y divided by r. Now, while I do have a complex fraction right here, I really should just flip and multiply. I also recognize that I have a fraction equal to a fraction, or I have a proportion, and proportions we know can be solved through cross multiplication. So I'm going to go the easy direction first. R times r is r squared. And in the other direction equals, I'm going to write this out simply first, 3y over x times y. And I'm going to simplify that right side. R squared is equal to 3y squared over x. R squared is equal to 3y squared over x. Very similar to example, I'll move that up for y'all. Very similar to the first two examples, we don't like fractions. So I'm going to get rid of that fraction by multiplying by x on both sides, leaving us with x, r squared, is equal to 3y squared. Okay, again, our goal will go from polar to rectangular. We've been able to get rid of the thetas and the trig functions, but you may notice we still have an r squared here. Well, r squared, unlike r, we have a direct substitution for r squared. R squared is equal to x squared plus y squared. And I still have the 3y squared on the right-hand side. Now, taking a look, we no longer have any thetas, trig functions, or r's. We only have x's and y's, which means this is a rectangular equation. Is this something you can type into your calculator the way it is now? Absolutely not. As disgusting as that original equation looked, in polar form, this equation, probably way simpler in polar form, as gross as this looked, I could easily get r by itself by multiplying both sides by the denominator, and I'd have a, maybe not pretty, but I'd have a polar equation that could easily go into the calculator. Our rectangular form, not so pretty. Now, I could play with this a little. If I really truly wanted to get, sorry, the lighting is terrible. If I truly wanted to get that y by itself, we could work at it. To get that y by itself, I could distribute that x. I could move the x squared terms to the other side. Heck, if you want, you know what, we'll go ahead and do it. X cubed plus xy squared, getting rid of those parentheses. I do have to distribute because of the plus sign, equals 3y squared. To get that y by itself, well, I got y's on both sides, never going to get y by itself if it's on both sides. So I'm going to subtract the xy squared to the right, which gives us 3y squared minus xy squared. Noticing on the right-hand side that I actually have this common y squared, I'm going to go ahead and factor that out. Oh, whoops, that should meant a parenthesis there. That gives us a 3 minus x. Ignore that equal sign I had in there. And I would divide both sides by 3 minus x, which gives us y squared is equal to x cubed over 3 minus x. And you know what? I'm actually, even though y is not technically by itself, I have that squared. That's probably the best or the most simplified form I can get. If I was going to put it in my calculator in rectangular form, I'd have to square root both sides. And in order to get the complete graph, I would have to make sure that I not only graph the square root of this nasty fraction, I'd have to also graph the negative square root. That way I get the complete graph. So again, this rectangular equation, not so fun to deal with, especially because of how we would have to put it in our calculator. So although this polar equation didn't look so great when we started, it's actually, in the long run, the easier way of expressing this equation right here. So at this point, I want you to practice converting in this direction from polar to rectangular. Again, there are more practice problems on the next slide. There are also practice problems in your book. Answers for the odds in your book are in the back of your book. And I think I wrote that out on this slide right here. Absolutely, answers starting on page A134, and slide 12 had some additional practice. The answer key for this one is posted on Canvas. Please make sure that you work some practice problems. Ask me questions. Feel free to email me anytime. And Monday, the 13th, during 0 hour, I will be having office hours. There's more details about that on Canvas.